Welcome everyone to the webinar that is sponsored by the IEEE CIS. This webinar is a part of a series of webinar offered to IEEE CIS member each year. And today we have Professor Kathleen Kasmalik, who is going to present autonomous bootstrapping of collective motion behaviors for swarm robot. And I will take this opportunity to advertise the next webinar will be in 22nd March, which will be generation hyper heuristic for automate design, configuration, and selection. So if you're interested, you can register for that. So now, thank you, Professor Kathleen. So you can give the presentation now. Thank you so much.
Thanks, Anthony. I trust that the slides are all visible on the screen and the audio is good. All right, thank you very much. And today I'm going to talk about swarming robots, and particularly I'm going to talk about how we can allow those robots to autonomously bootstrap their own collective motion behaviors. I might start a timer as well so that I can keep track of how long I'm going. So this work is done by a whole team of people. So we have students on the project and also postdocs. We've got a team of collaborators at UNSW Canberra and also from Defence Science and Technology Group. And the work is funded by the Australian Research Council, and parts of the work also been picked up as a Defence Science Partnering Deed. There's quite a few people have done input into the work that's behind the slides I'm presenting today. So I'll start off with some research motivation. So these are pictures that the team has taken from around our local area. So you can see that in nature we have many different types of flocking birds and swarming insects, and they've evolved all sorts of different collective behaviours. So here we have some ducks on a local lake that are moving in a formation. We have some ants here that they're sort of moving from left to right across the screen, but there's also this area of interest in the middle that they're gathering around that area of interest. This one over here is a heterogeneous flock, so we've got two different types of birds that are foraging. We actually threw some seed there and they're eating from that. And some of the birds are eating, and you'll see some of them will put their heads up and have a bit of a look around to make sure that there's no threat in the area. So different behaviours and different animals there. And this picture in the middle, you can see an example of collective nest building. So this is a wasp's nest, and you can see that characteristic repetitive hexagonal structure there that they put together. So all different behaviours that have evolved that are useful for the survival of these flocks and swarms. And some of these behaviours are actually quite easy to reproduce in a computer simulation. So this is just a point mass simulation made with, you might have heard the term boids. And you can see that it's quite easy to put together some of these different shapes here. So we've got this undulating movement in lines. We've got these more grouped flocks here on the screen. And with some small modifications of the parameters, we can make some even different types of shapes that start to look perhaps a little bit more artificial, but still have some of those grouping and ordering characteristics, alignment characteristics. And so there's another one here that's, this is more what you might see in a fruit fly or something like that, that aggregating behavior. So these are quite easy to do in a computer simulation. And I have here just a little refresher on some of the maths that's behind that, because it's useful for understanding the rest of the talk. So if you have a look at these triangles here and imagine that these are those point mass boids that you saw in the previous simulations, I'm going to talk through what happens for this black one in the middle here. So essentially all the boids are controlled by three forces for cohesion. So the group should try to stay together. Separation, so that the group should try not to run into each other while they're staying together. And alignment, they should all try to move in the same direction. So what happens is this boid in the middle will have a look within a certain radius at the boids around it, and it will see all of these red boids here. It will compute the center of mass of its neighbors, and it will then compute a force towards that center of mass. So the next thing it will do is look within a slightly closer radius, and it will see which boids are in that radius and compute the center of mass. And this is a separation radius, so the boid will steer away from that centroid there. And finally, it will do one more calculation to align itself with the boids, and generally we use the same radius here. There's our separation force, and there's our alignment force. So it will take the average direction of the boids around it. So once these forces are calculated, they're combined as a weighted sum, and that allows the boids to move in some of the patterns that we saw earlier. And I'll just point out these weights here because that's the part that's going to be important for us when we're trying to bootstrap these equations. So this maths, we can actually take, again, relatively easily, and we can apply it to agents that actually have real physical constraints like these robots. So this, I say relatively easily, because now these are not point masses anymore. So they have a radius. We need to make sure that they stay a bit further apart so they don't run into each other. They also can't turn on the spot quite as cleanly as a point mass. So they have a particular turning circle. And in practice, it is possible to get them to make these nice formations like this, but it's definitely a little bit more fiddly. So need to really experiment with those weights that I showed on the previous screen to really make sure that they're not going to run into each other, and they're going to avoid the walls, and they're going to stay together. So it's quite fiddly. But it can be done. So now I go to the motivation for the rest of the work that I present in the slides. So imagine now that we have many different types of cheap robot platforms available. And this is really the world that we do live in now. There are platforms that can go on the ground. There are platforms that can fly. There are autonomous vehicle platforms that will work underwater. And if you even consider the ones that work on the ground, some of them have wheels, some of them have tracks. There might be 2 wheels, 4 wheels. There are legged platforms. So there's many different types of platforms available, and they're getting cheaper and cheaper. So we can imagine that in future, a company might have all sorts of different robotic platforms sitting in the cupboard ready to go on a mission. And essentially what we'd like to be able to do is that they can put a selection of those vehicles onto a truck. They can take them out to the site where they want to do their mission. And then we put the robots into a small training area so that they can bootstrap some useful formation behaviours and collective motion behaviours. And then they can supply those to the human operator who will go off and do the mission. So this is sort of what we're hoping to be able to do in the future. The robot platforms are already available, but at the moment we still have the difficulty that when we get these robot platforms off the shelf, we need to retune all the different formation behaviours. So ideally what we'd like to be able to do is put the robots in a test area. They can make their own collective motion behaviours and then supply those so that we can actually go and do the mission. So that brings me to the overview of today's talk. So a number of different things that we need in order to meet the vision that I've just described. The first thing is that we need the machine to be able to recognize collective motion when it's occurring. So I've shown you that it's possible and even easy in some cases to make simulations or robots that move in a formation. But actually recognizing that that's going on is a slightly different question and is somewhat more difficult. Once we have those techniques for recognizing the collective motion, we then need a framework to embed that in so that we can generate different motions on the fly and test them to decide if they're the type of motion that we want and then keep the good ones. So I'll talk about both of those things and a couple of different alternatives for those today. and then look at some examples in action as we go. And I'll talk a little bit about the human-machine teaming piece as well, just to give you some examples of things that we think might be useful for that in the future. So firstly, how can a machine recognize a collective motion? As I mentioned before, doing the collective motion is not that hard, but for the machines to actually recognize that they're engaged in that collective motion while they're doing it is a completely different question. So we thought that there might be two ways that this could be done. So perhaps we could provide a labeled data set and we could supervise a machine so that it's able to learn how to recognize a collective motion the same way that a human does. So that was one approach. And obviously there's all of the normal limitations of supervised learning is, okay, well, we need a data set and that data set is going to be limited to a certain type of data and so on. So we thought that there's possibly also another way that we might be able to do this, which is an unsupervised learning of the collective motion. So just recognizing structure when it's there, rather than having to be trained in advance. So the talk today, I'll have a look at both of these things. So I'll go through first the supervised piece and then look at the unsupervised piece later on. So supervised learning, how can we train a machine to recognize collective motion in the same way that a human does? So what we thought we could do is start with a survey. First, we wanted to understand exactly how humans recognize collective motion. So this particular survey is still available online and you can go and have a look at it if you're interested. Essentially, once you click through all of the front matter and the permissions and so on, you come to a screen that looks like this. So this screen has some different collective motions that are short video clips. And then there are a bunch of sliders that allow the participant to give their opinion of whether they think that this video is a flocking behavior and whether the boids in it appear to be aligned or whether they appear to be grouped. And essentially before this happens, there's a short tutorial to give an introduction to some of the concepts that are in the survey. So our initial release of the survey, we had about 90 participants in this. And what they did was provide us these slider results. And what we did behind the scenes from our simulation was collect information about each of the 200 boids that are in the video. So we generated these videos from a simulation software. And so we had access to all the data about the velocities of the boids, the cohesion forces, the alignment forces, the separation forces. And we could also tell how many boids are in the neighborhood of any other boid for the different radiuses that I talked to you about earlier. Essentially, we collected everything we possibly could about these videos, and then we also collected the human label from these slider values. So I've got on the right-hand side here a list of the steps that we took. So I've already explained how we extracted those features from the video. And the next thing that we did was we computed the average human opinion of each of the videos. So the opinions, we had 3 different opinions about whether it was flocking, aligned or grouped. And this chart here shows you what people said about each of the videos. So we actually had 16 videos and we gave them some names so that we could remember which was which. And we had some of them that we had drawn from a previous paper that had some special names that we thought people might think that those ones were actually a flocking behavior. And we had a bunch of random ones where we thought, okay, people probably will think that those were random. Overall, you can see that people generally had a similar opinion, but in some cases their opinion differed. So these higher bars here indicate that people thought that those videos were not flocking, not aligned, and not grouped. And these lower values here indicated that on average, people thought that these videos showed behavior that was flocking, aligned, and grouped. And you can see that there are some videos where there might have been a difference of opinion. So this one here, people thought it was not grouped, but they thought it was still this kind of flocking behavior. So we were able to get a few different statistics from there. The next thing we did with each of these values was to apply a step function, and that gave us a binary label. And we could apply that binary label to every set of features that we extracted from the video. So that data set is actually available on the UCI repository. And essentially there's 16 different behaviors, each with 1,500 features per video, and they're all labeled with the average human opinion of whether it was flocking, grouped, or aligned. So from taking this labeled data set, we're then able to see if we could train some machine learning algorithms to recognize the flocking in the same way that a human does. So what we did for that was we chose a bunch of different machine learning algorithms from the MATLAB toolbox, and we trained them, did a fairly standard 5-fold cross-validation with some of those different learning algorithms. So 2 different neural network approaches, a decision tree approach, naive Bayes, and a support vector machine. We found that the neural nets and decision trees were able to learn very accurately to recognize flocking behavior in the same way that the human does, which makes sense. It was a nonlinear problem, and these algorithms are good at that. The decision tree is the quickest of the approaches. And so this one seemed particularly promising to us as a way that we could actually have a module that can recognize how to classify flocking or not flocking. And obviously you only need to train that once. So once you have the data set, once you have a decision tree, you can then go ahead and use that in another setting to tell you whether a particular behavior that it hasn't seen before is flocking or not flocking. So then the next question for us is, now that we have one way that a machine can recognize collective motion, what to do with it? So how do we actually use that so that the machine can generate the collective motion and decide whether it's a good one or not? So whether there's a structured flocking behavior or not. So we actually came up again with 2 ways. There may well be other ways, but this is where we started on the project. So we had a reinforcement learning as one approach and evolution as another possible approach to essentially this bootstrapping of collective motion behavior. So I'm going to talk first about the reinforcement learning, and then I'll have a look at the evolutionary part after that. Just moving some things around on the screen here. Okay, so this is our framework. It's a developmental framework, so that means that it's a system that starts initially with no behaviors, so no useful behaviors, but it has structures in it for learning different behaviors. And specifically in this case, it's tuning collective motion behaviors. So the 2 frameworks that I'm going to show both have this characteristic dual cycle approach. So the blue cycle on the right-hand side is what we call the robot-centric cycle, and I've just indicated that with the video here. So this is really the try it out cycle. So you can have either a simulation like this one to try it out in, or you might have some simulated robots to try it out in, or some real robots in the field. But this cycle is representing the agents as they're sensing some parameter values, and then they're using those to go and do some flocking. And so the parameter values that they're sensing in this case is those weights that I talked about earlier, things like the maximum and minimum velocity of the agent in question, the radiuses that I talked about earlier, a vision angle, and some probabilities of how often the different rules will be applied. So we can initialize those parameters, for example, at random, and we can then allow the agents to try it out. After they've tried it out, they will send their behavior parameters through to the left-hand cycle here, and this is the learning cycle on this side. So they send their parameter values through to the learning cycle, and this then calculates a reward. And that reward is calculated using the module that I described to you before, so the decision tree module that I described before. So that the behavior features will be passed into the decision tree. The decision tree will decide whether that was a flocking or non-flocking behavior, and the agent can then learn from that, and the cycle continues. So this decision tree here, so I described a trained tree earlier. We found that the trained tree was actually quite large. It had about 1,000 different rules in it. That was a little bit slow for using in a cycle like this. So we actually pruned that decision tree down to just over 70 rules. And we found that that was a good trade-off between accurately being able to detect a flocking or not flocking and being able to do it quickly. So this is your reinforcement learning cycle on this side. So the next couple of slides show some tuned behaviours that came from the system. So you can see this one here, you sort of get a grouped behaviour, and this is an analogy from nature. Most of these videos, I have to say, are from my backyard. So I didn't have to look hard for these behaviours. They were all out there in the very local neighbourhood. So this is one that looks a little bit like these fruit fly here that are in the compost. So that's tuned from a random behaviour. And then there's another example here. I'll let that one converge. And you can see that there's now this movement in a line kind of behavior. And again, this is another one from my backyard with the ants moving in a line there. So these were essentially from the framework that I showed you 2 slides ago. We input some random behaviors, and we allow the system to then modify the weights of the swarm with the feedback from that decision tree that's trained on human perception. And these are the sorts of behaviours that we then get out of that system, which we thought was very nice. That was certainly nice to look at. And then our next question was, okay, well, they're quite nice to look at, but overall, can we quantify what's actually going on there? So this slide is starting to present some metrics for putting a number on how the system is working. So what we have on these 2 charts is some very traditional group and order metrics for evaluating swarms. So grouping measures the average distance between individuals in the swarm, while ordering measures the average difference in alignment between individuals in the swarm. These are only indicators of whether swarming is occurring, because as you've seen from the examples that I've given, there are some swarms that are quite well grouped, but they're not ordered at all. There are others that are grouped and ordered. There are others that are ordered, but perhaps spread out much further. And we've already seen that humans will identify different combinations of these as flocking, but there's sort of no hard and fast rules that the group and order metrics have to be within particular ranges. So these are really indicators rather than a be-all and end-all. But just to give you an example, you can see from 8 chosen random motions, so that's these black lines here, the higher value of the grouping means that there was greater distance between the individuals in the swarm. And then you can see the tuned behaviour that came from the reinforcement learner interacting with the swarm. And you can see that in many cases, the grouping value has decreased. That means that the agents are closer together. And in cases where perhaps the grouping value didn't decrease, so this one here is an example, number 7, you can see that perhaps the order value decreased in that one. So it just gives you an example of how the random input does determine somewhat what kind of an output we're going to get in terms of a tuned behaviour, but the system is capable of tuning different kinds of behaviours from the different inputs. And we get a good diversity of behaviours. So some of them were sort of moving in a line, some of them were aggregated, and so on. But the system is having a significant input, or a significant impact on those group and order values. So that was a way that we could look at that and have a clear idea that it was actually doing something significant. Okay, so having a look at the next part now of the presentation. So far we've had a look at really what I like to call the intrinsic motivation. So we've looked at building a system that is able to develop these collective motion behaviours. So moving in a group, aggregating in a group, moving in a line, but there's no specific mission in any of those situations. It's really just bringing the agents together in a formation. Of course, what we said at the beginning is that we'd really like to be able to have a specific mission objective. So what about when we do that? What can we do? I showed you one example of a format before where the behaviours are just given to the person via an interface and they go off and do what they want with them. So here's another example where we're actually going to permit the controller to input some extrinsic goals at the time of training, so that we can have robots that are trained with their self-bootstrapped collective motion behaviours, also taking into account a human objective. So it's essentially put the human a little bit earlier in the loop so that they can input some extrinsic reward at the same time the agents are working with their intrinsic reward to bootstrap their behaviours. So let's have a look at this framework again. So this is the same one I showed earlier, but just indicating where the human is now sitting in the loop. So the human here is able to input some extrinsic reward that will be combined with the intrinsic reward for the structured behaviour. And then that will be used by the agents as they're training themselves. So we started quite simply. So our first two, we thought, okay, some simple ones are gather at a target and avoid obstacles, all while doing these collective motion behaviours. And essentially then we trained the system the same way that we did before. So we gave it some random behaviours and allowed it to tune those behaviours using a combination of the decision-tree reward signal and the human extrinsic reward. So a few more videos here showing some tuned behaviours. So this example is specifically sort of seeking the target behaviours. So I've got, again, the example from the backyard here. So this is the ants aggregating around the corn. And here we have the couple of examples of tuned behaviours from the reinforcement learning system. And you can see once again there's a diversity of different behaviours that are solving the problem in a different way. So on the left you can see that the agents have sort of gathered all to one side of the target, whereas on the right you can see that they've gathered more of a distribution around the target. So these are some of the characteristics of this tuning system, is that when we put in different starting points, we'll get different tuned behaviours from the starting point. And essentially the idea is that all of these different behaviours would go into a library and the human operator can then select from that library to use those for whatever mission they're going to be doing. So I wanted to talk a little bit about this human swarm interaction piece. So this was work done by an honours student in the last year. So essentially she worked on developing an interface for interacting with these swarms that have been tuned. So you can see on the right of the interface, there's actual, these are the boids here, and we imagine that in future they might be representing robots in the real world. You can see she's using her right thumb there to place breadcrumbs on the screen. So in our model, the boids there are controlled by different flavours of breadcrumbs. So some of the breadcrumbs will have a come here kind of a flavour, and some of them will have an avoid this kind of a flavour, and others might have a move into this formation and do that kind of a flavor. And that's where the library of behaviors would come into the system. So all of those self-tuned behaviors would appear in a library that could then be used by the operator. So that's what's happening on the right-hand side of the screen. On the left-hand side of the screen was actually the part of the project that she was focusing on, and it was looking at what kinds of metrics can we show that give indicators of the quality of the swarm performance that's happening on the right. So she looked at a bunch of different traditional metrics. So I've already described the group and order metrics before. She had a fragmentation metric to give the operator an idea of whether the boids were all clustered in a single group or whether there were multiple groups of them moving around in the area. There was another one just below there that was a coverage metric, so giving an idea of how much of the area that the group had explored together. So her project was building this system, and then there's another interesting piece of work that we can do to try to understand the usability of the system. There's obviously a lot going on because the operator has to be able to place these breadcrumbs to control the swarm, and they also might be looking at some of these metrics to understand whether the swarm is doing what they want it to do. So there's quite a few interesting projects coming up there to look at that user interface and how that's going to work. This slide is now looking at another aspect of the system. I've obviously talked a lot about the point mass boids in the last few slides, and where we'd like to be is to transfer these ideas onto real robots that have real physical constraints. I'm going to have a look over the next slides at some different ways to do this. The first thing we had to think about, or we've started to have a think about, is essentially a direct application. So can we take the system that we've developed on the point mass data and apply it directly to robots? Now, obviously, there are going to be some key limitations of that point mass data. So the movement of the point masses is quite fast compared to the speed that a regular robot can move at. So some of those branches in the decision tree are going to be invalid as a result. And what we found was, in fact, it didn't make a good transfer in its raw form. So we actually collected a little bit of additional data from some robot simulations. So again, with a human labeling. We did an expert labeling in this case rather than a layperson's labeling. And we used that to perform a transfer learning to transfer the decision tree. Essentially, we pruned back the decision tree and then allowed it to regrow with the new robot data. And you can see here that we're able to achieve something that looks a little bit like some of those point mass swarms. It's definitely not as beautiful. So you've got some of the robots that are running into each other there, and the alignment is not quite as good. But we had some success with the transfer by doing that. Obviously, one of the key constraints of the technique is that when it's trained on the point mass data, there are very specific features like the velocity that aren't going to transfer well to the robots. And so we have this question: do we maintain the decision tree approach, which is very, very quick? So once you have a trained decision tree, they're very quick to be able to label whether something is flocking or not flocking. Or is there another way that we can do this where we don't need to collect that human labeled data in order to make a decision whether a group of robots is flocking or not flocking? And our alternative approach is, as I mentioned earlier, an unsupervised learning approach. So what if we don't label the data? So in that case, we still have our features extracted from the videos, but let's now throw away the labels. So let's assume that we do not have access to the humans to tell us whether they were flocking or not flocking. So we had a hypothesis that if we took that data, excuse me, and fed it into something like a self-organizing map, which is able to recognize patterns, we had a hypothesis that the error of the map would be lower if it was taking data from structured motions. And the reason for that is if you imagine yourself walking in a crowd and you think, okay, ahead of me I've got people, to the left of me I've got people, to the right of me I've got people. Now imagine someone next to you walking in the crowd. Well, they're seeing the same thing. They're seeing ahead of them there's people, to the left of them there's people, to the right of them there's people. So that there is structure between what you're observing and what the person walking next to you is observing. So our hypothesis was if we fed data from the boids into a self-organizing map, boids that are engaged in a collective motion would result in a lower error in the self-organizing map. So we fed the input in, we record the quantization error of the self-organizing map, and we look for groups of boids that are having a low quantization error. Now, the downside of this approach, I'll mention up front, is that a self-organizing map needs to observe a swarm much longer than a decision tree needs to observe a swarm. So we were finding that a decision tree can make an accurate decision from only 10 time steps of data. In contrast, self-organizing map needs to observe around 1,500 feature vectors before it can make a reliable prediction of what the error is going to be. So here is some example, an example of the kinds of output that we can get from a decision tree, from a self-organizing map, when we're trying to decide whether something is flocking or not flocking. So we did this experiment using our same set of swarming and random examples that we had earlier. And we fed 1,500 instances of each of these into a self-organizing map and recorded the average quantization error after that time. So you can see that the ones that we identified as structured motions, and humans tended to agree with structured motions here, tend to have a low quantization error, whereas some of the others have a high quantization error. You can see that this system wasn't perfect. So there are certainly some where some of these ones that humans identify as structured have quite a high quantization error. But overall, quite a few of them had a low quantization error. And we felt that there was enough there that we could continue to have a look at that technique. So we actually looked at this technique specifically within an evolutionary framework. So you can see again, this framework has the same characteristic dual cycle approach as our reinforcement learning approach. So on the right, we have the robot-centric cycle or the try it out cycle. So this is where you've got either your simulation or your robots trying out some different parameters. On the left here, we have the evolutionary cycle. So this is doing your traditional parent selection, crossover, variation, mutation, and replacement. And then in the middle, once again, we have the artificial value system. So this component here, we could have used our supervised learning decision tree at this point here to decide whether a particular phenome is representing flocking or not flocking configuration. But as I mentioned, we wanted to have a look at an alternative approach, which was our self-organizing map approach to identify whether there's structure or not structure. Now, we had to do quite a few different investigations at this point because there's obviously quite a few different types of data that we can take from the agents as they're moving around in their flock. So you could take the data from each boid individually. So for the one I described in terms of humans, for example, we could take the data from me, we could take the data from the person standing next to me, and we could feed that in individually. Another approach is that we could take the data from me, we could take the data from the person standing next to me and all of the other people, and we could catenate that data into a single string and feed that into self-organizing map all as a single string. And then, of course, the question is, regardless of whether we do it boid by boid or all together, what data do we actually put in there? Do we put in the weights of the velocities of the agents? Do we put in the positions? Do we put in their cohesion and alignment forces? It's not immediately clear which of those data might be the best for actually evolving the different behaviours. So we actually looked at quite a few different approaches. We looked at whether to normalise that data or not normalise that data. And the design rules that we came up with, which are conclusions of this paper, that it's best to go in a boid by boid manner. So we feed the data in from one boid at a time. And it's also best to normalise that data as well. And this gave the most accurate information where we were able to pick a threshold that was clearly between those that were flopping and those that were not flopping. So you can see that happening in this example here. So this is our tried out loop, and this is our evolutionary loop here. So this value function here then is a self-organizing map that's taking information about the positions, velocities, cohesion, alignment, separation, forces as input, and it's then using that to select which of the individuals are going to be driving the evolutionary process. So next couple of slides, again, some behaviours that are now, these are evolved behaviours rather than learned behaviours. Key differences of the evolutionary system: rather than tuning a single behaviour at a time, we're now producing a population of behaviours at a time. The downside of the approach is that it's much slower. So the evolution needs to observe behaviours for much longer before it's able to calculate fitness. And because there's 50 individuals in a population, that takes time. But we were able to achieve, again, quite a diversity of different behaviours from the evolution. So you can see some of these moving in a line type behaviours and some of these grouped behaviours that are being evolved by the system. And there's a very limited human in the loop in this system. Essentially, the value function here is just looking for structure. So there's no human labels at this point here. The system is just looking for structure from the experiences of the boids in the simulation. So once again, we wanted to have some quantitative data to back up some of those videos. And again, we looked at the group and order statistics to give us indicators of what was going on. And we did experiment with quite a few variants of the fitness function. As I mentioned, depending what information you feed into the self-organizing map, depends what is actually going to be evolved by the swarm. So when we fed in information about the velocity of the agents, for example, the evolutionary processes tend to tune for alignment, whereas when we fed in information about the relative positions of the boid, the system tends to tune more for grouping. So there's certainly some biases there, and there's also opportunity that we can potentially feed in both of those data and see some different types of behaviours emerging from the system. These curves here are showing the mean quantization error of the self-organizing maps over 100 generations in each case. And you can see that that does significantly decrease over time. So the evolution is changing the behavior of the population over time. One thing that we did find is that the behaviors in these later generations had lost a lot of the diversity that we saw in the earlier generations. And certainly there is a piece of work to do on stopping criteria for the evolution. And we believe that that is linked to understanding the quantization error that provides a good trade-off between the different types of behaviours. So what we found overall is that the stopping the evolution between about 40 and 60 generations was producing populations that had some good structured characteristics like the ones I showed before, but also maintained a diversity of different types of structures in the population. So just some conclusions now from the work. We concluded that the machine can be trained to recognise structured collective motion, and it can do this by training it with some human labelled data, or there's potential to do this in an unsupervised manner. So just looking for structure in the experiences of the agents. And the machines can use this recognition ability to generate libraries of collective motion behaviours. So we were able to do this in two different ways, by evolving populations of diverse behaviours and by using reinforcement learning to tune different behaviours. And we were also able to learn the structured behaviours only, or the structured behaviours in the presence of an extrinsic goal, such as searching for a target. A really wide range of areas for future work have come up from the project. So I've been pointing things out along the way where we need to keep working on some of those areas. One of the things that has been a characteristic of most of the work we've done so far is a centralized value system. So even when we're looking at the experiences of individual boids, we've been sending that to a centralized value system. So whether it's a decision tree that's been trained on the human labeling, or whether it's a self-organizing map, we've looked at just a single one of those in each case. So obviously nowadays there are quite a number of machine learning algorithms and architectures for distributing machine learning algorithms. So there's potential to make distributed versions of the frameworks that I've presented today. The transfer step onto real robots is another area for future work. So certainly exploiting the transfer learning is one option, or further investigating the unsupervised learning as well. There are other alternative approaches as well. So looking at structured motion from video data is another one. So if you imagine from all these platforms of robots that we've got, we might have some flight vehicles that are able to carry a downward pointing camera. If we could recognize the structured motion from that video data, then that would be another way that the individuals could decide whether they're flocking or not flocking. And then there's the human swarm interaction piece as well, where there's a lot of potential for future work too. So thank you very much for the opportunity to talk to you today. And I'll be here to answer any questions that you might have as well. So please send them through.
Okay, thank you so much, Kathleen. So if you have any question, you can type in the question box. No. There's no question at all. Okay, Kathleen, okay, that one question from the audience from Matt Henry. He asks, can you elaborate on the reward function you use in RL and EC?
Yeah, so the reward function in the reinforcement learning was based on a decision tree that had been trained with the human labeled data. So essentially we built the decision tree by feeding in the human labeled data. We then pruned that decision tree back down to about 70 rules. The decision tree then gives essentially a yes/no value on whether something is flocking or not flocking. We then applied a function to that where yes was something like a reward of 100, where no was a 0 reward, and then that became the reward function for the reinforcement learning. There was certainly some tuning that we had to do with that reward function. So getting the values right, we had to make sure that the the best flocking approaches had the highest reward, whereas others had the lowest feedback. And we used that in a deep reinforcement learning setting. I haven't explained that well, but I guess the things that the decision tree recognised most strongly as flocking needed to be given the highest reward. In the evolutionary approach, it was a fitness-based reward, but still numerical. In that case, we used directly the quantization error of the self-organizing map as the fitness.
Okay. And next question is from Ayat Al-Matui. He said, do you think we can apply this method to aerial vehicles?
The aerial vehicles?
Yeah.
Yeah, so we certainly haven't ourselves looked at anything in 3 dimensions. The boid rules in 3 dimensions are quite similar. There's just another dimension. There's obviously then the issue of the agents running into each other. When they're on the ground and they run into each other, it's not such a problem. When they're in the air and they run into each other, they crash. And both of the techniques I've described today are trial and error techniques. So both the reinforcement learning and the evolution are trial and error techniques. So there would need to be significantly more constraints in the system to stop catastrophic outcomes while the agents are in their experimental mode that are not quite as necessary on the ground vehicles.
Okay. And next question is from Scott Gerard. He asking, what kinds of missions would be best to use your approach?
So this project, we've been specifically interested in transport type missions. So getting a group of vehicles from A to B while they're carrying a load. Swarming is very nice for that because when the agents are in a nice formation, they travel more efficiently, they use yet less fuel, and they also stay together as a group. So we imagine that some of these different configurations will be good for different transport in different types of environments. So when you've got room, you can have a more spread out formation. When you're in a cluttered, maybe an urban environment, you would need some of the narrower, closer configurations. So that's the sort of thing that we're looking at the moment with the collective motions. We have had a little look at coverage problems as well. So coverage problems, you would like your agents to visit all areas of a particular environment over a certain time period. We did a small investigation where we were looking at how effective some of these grouped behaviours were for doing coverage compared to just a bunch of agents moving at random. And we did find that when they're in a group, the agents will cover the environment more quickly. Essentially, you can imagine if they just spread out in a blob and move across the environment, then that's going to cover the whole thing very quickly. Whereas if you've got them dodging around all over the place, it will take a little longer, although they will get the job done. So those are the sorts of things that we've been looking at so far.
Okay. And question from Jenny Lee. Thank you for the fabulous speech. I got a question on what specific evolutionary algorithm did you use?
We used a genetic algorithm with a diversity metric in it. So we were specifically wanting to create not just a population that converges on a low quantization error, but a population that maintains diversity while converging. And the reason for that is that our ideal future scenario is that you'll simply take the population after a set number of generations, and that will become your library of behaviours that you can use on the next mission. So genetic algorithm with a diversity measure.
Okay. Next question is from the same Matt Henry. He said, was the reward based on an action select for forecast swarm behavior or just detection?
Can you repeat the question?
Was the reward based on an action select for forecast swarm behavior or just a detection? It's like
I'll
the
just give
action
a
is.
little bit more. I can give a little bit more information about the reinforcement learning setup, I guess. Maybe I can flick back to the slide even. Where are we? Here we are. So at this point here, what the system is able to do is perturb these parameters. So this is the state space here, which is the weights, the velocities, the radiuses, the vision angle, and a couple of other rules that you can see in the literature. Essentially, the actions here are to make perturbations of each of these values. So perhaps it will increase the separation weight, or perhaps it will decrease the cohesion weight, or increase the separation radius. So each action can perturb one of these parameters by a small amount, and then this cycle will try out the new set of parameters. And the data about the behavior of the robots, so that's now your B data that I showed earlier, which was the velocity, the cohesion weights, cohesion forces, alignment forces. This is passed into the reward function, which then essentially assigns a quality value to that behavior that's fed into the learning part of the reinforcement learner.
Okay. Yeah, I think that should answer his question. Next question is, what is your advice for people who are just starting in this field, like what to stick to generally?
I think this is it's a really interesting and emerging field. My advice is to stick to what you love. You know, there's so many different sub areas of this field. So I mentioned at the end that we need to look at distributed versions of this, for example. The thing that I really love is actually these reward functions and how to design these. So we've made curiosity models, we've made fitness functions, we've made some reward functions. That's the part that I'm particularly interested in doing, and where my focus is. So many different things that you could do, though. There's new versions of this framework that are using different learning approaches. There's really looking at the deep learning literature that could underlie this part of the cycle. There are different evolutionary fields. So yeah, my advice is stick to what you love and focus your work on that particular area.
Okay, and again from Matt Henley, he asking, the human input introduced new constraints. How did detection of aggregate swarm behavior contribute to respond to those dynamic constraints?
Can you ask the question again?
The human input introduced new constraints. How did detection of aggregate swarm behavior contribute to respond to those dynamic constraints? I think he asking how did your swarm robot respond to the new constraint that introduced by human, I guess.
I guess again I can just give a little bit more information about this part of the work. So the data that we had from humans in this part of the work was collected offline compared to what was going on in this part of the work. So this survey, when we ran it, this was one of the earliest things that we did, was run this survey to collect information about people's perception of swarming. We chose just 16 different videos, 8 structured 8 unstructured, or what we thought would be 8 structured, 8 unstructured, that covered a broad range of different types of structured motion, including the aggregated, dispersed, moving in a line structures. So in that sense, the reward signal that sits at the heart of both of these models is capable of identifying a range of different types of behaviours as flocking. So that allows the system to actually learn a diverse set of potential behaviours as the output.
Oh, he said that I was asking about a human-machine interaction via the interface in this case.
So that was a little bit later. So what are the humans able to do with the system?
Yeah, human-machine interaction, that's what he's asking.
Yeah, so at this point, the interface that we've designed has a group of different pre-programmed controls. So these are our breadcrumbs. They sort of come here, go away, move like this kind of breadcrumbs. What we would like to do with this system is essentially, you see this blank space here. We would like the system to put the evolved behaviours, add them into these blank spaces here, so that the human not only has access to these breadcrumbs, but it also has access to all of the different types of collective motion behaviours that have been bootstrapped by the agents. So that there's various bits of research that we have to do to make that happen. Essentially, we're going to treat it like a game, sort of procedural content generation of the interface of the game, so that the different buttons will pop up as the agents actually bootstrap their behaviours.
Okay. This question is from Scott Gerard. He asking, have you done any experiments where the state space is a graph, not a full plane? A collection of a city street would become the graph. That's what he asked.
I wonder if that question is asking sort of more about abstract swarming than swarming in a physical 2D space, in which case the answer is no, we've only focused on 2D spaces.
Okay, and last question from Matt Henley. Can you elaborate on the intrinsic motivations you investigate in RL and EC?
Yeah, I guess the key intrinsic motivation that we looked at is essentially a curiosity model. So the self-organizing map forms the basis of many curiosity models that have been used in single agent systems. So basically the idea is the self-organizing map gives you information about the similarity and recency of experiences. And when the error of that map is getting smaller, you know that they're experiences that have been similar to things you've seen before and you've seen them recently. So that model is sort of one that we've taken from the single agent literature to use in this system. We are using it in a slightly different way because it's now collective motion and there's multiple agents feeding their data into a single network. But yeah, that's probably the key example.
Okay, thank you. Oh. Okay, Matt Henley said thank you for answering all his questions.
No worries.
I think we are at the end of the webinar. So thank you so much, Kathleen, for giving a wonderful talk and interesting talk. And good night, good day, everyone. So goodbye.
Bye.
Have a nice day.